intersection with the results for the individual f's. And once we have this intersection, this will then be our new value for y. So actually not a lot of difference compared to Buechi games, just one additional loop over the different sets that we would like to reach infinitely often. Strategies for generalized Buechi games are a bit more complicated, but in the exercises you are in the lucky position that you only have to implement an algorithm for Buechi games, not for generalized Buechi games. For the strategies, the situation, the picture looks like this. Remember, for normal Buechi games, we just had this green part here. These two things did not exist. And what we did is, from y something, we were getting closer and closer and closer to our target region, and then back, and then closer and closer and closer, and then back, and then closer and closer and closer. And this way we reached f1 infinitely often. Now we have several copies of these onion rings for each of our different set of target states that we need to reach infinitely often. Once this fixed point formula is terminated, then from this pink region, orange, yeah, we can reach this, we can reach this, and we can reach that, because this orange region is actually the intersection of the winning regions for these three reachability games. So if we are in orange, then we can decide either to go in here and reach f1, or we can decide to go in here and reach f2, or we can decide to reach f3. Now, the problem is that we would like to reach all of them infinitely often. So the simple strategy of going always in the air is not good, because then these other two are starving, basically. So, in a sense, what we have to do is we introduce a little bit of memory. Namely, if we have n such copies, we need a memory that can take n different values, and the intuitive meaning of this memory is, if the memory is set to 2, then this means that we should reach f2 next. And if the memory is set to 3, then this intuitive meaning is that we should reach f3 next. Now, our strategy looks as follows. So the initial memory content is completely arbitrary. This is just where we start. What we do is, if our memory is m, let's say 1, then we will go closer and closer and closer and closer to f1, and then back to y, this pink region. And while we go back to y, we update our memory. We just increment it by 1, saying that, okay, now we have reached f1, but now our next goal should actually be to reach f2. So we go back, update our memory, and since our memory is now 2, this means that we will reach f2 next. So we will now follow the strategy of getting closer, 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 closer to f2. And once we have reached f2, we go back and update our memory, saying that the next goal should be to reach f3. So we go here, closer, 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 back, and once we have reached f3, our next goal should be to reach f1 next. So this is what I mean here with by +1 with a wraparound. So if the counter overflows, then we just start with the lowest number again. So intuitively, how our strategy would look like is this. With memory 1, we get closer, 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 closer to f1. Then we go back to the peak region, but update our memory to 2. And if our memory is 2, then we are getting closer, closer, closer to f2. Once we have reached f2, we go back to pink, but with updating our memory to 3. There we get closer, 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 closer to 3. Back to orange with updating our memory to 1. And if we follow this strategy, you will see that we reach f infinity, f1 infinitely often, f2 infinitely often, and f3 infinitely often. So the trick here is that we really need to have memory. If we just base our decision where to go just on the state, then we cannot distinguish between these three cases what we would like to reach next. We would always reach the same f next. And then we reach f1 infinitely often, but the others not at all, and this is not good. That's why we introduce this memory to switch between the different targets that we would like to reach next. So this is the trick for computing winning strategies for Buechi games, and I also tried to define this in an algorithm. It's not particularly nice, but just makes things more explicit and more clear. But the important thing is that you understood basically this picture, that we need memory so that we can really alternate between these three goals. And this means that time is over and the lecture is also over. So to summarize, we have discussed algorithms, how we can compute winning regions and winning strategies for these 4 kinds of games. You do not yet know what to do with the resulting winning strategies, but this will be the content of the next lecture. Next lecture you will see how you can really implement these strategies then in form of circuits, for instance. And that's it. I still want